Welcome to the course on the role of international standards in fostering a circular economy. The circular economy is a continuous, positive development cycle. It aims to decouple consumption and production from natural resource use by preserving and enhancing natural capital, optimizing resource yields, and minimizing system risks by managing finite stocks and renewable flows, while reducing waste streams. A circular economy is restorative and regenerative by design, and aims to keep products, components, and materials at their highest utility and value at all times, while reducing waste streams. It achieves this through reusing, repairing, refurbishing, recycling or sharing existing materials and products as long as possible, thus extending the life cycle of products. This extension of the life cycle is what reduces waste to a minimum. When a product reaches the end of its life, its components or materials are kept within the economy and are used again wherever possible, thereby creating further value. In this way, when the end is also the beginning of another process, one can carry on infinitely, like a loop that reconnects back to itself. Under the traditional linear economy, the threat of e-waste has become significant in most countries due to the enormous uptake of information and communications technology, ICTs. This is because a linear economy works on a take, make, consume, throw away model, using large quantities of cheap, easily accessible materials and energy to make products that are then discarded after use. Planned obsolescence is also a concerning feature of a linear economy. It occurs when a product is designed to have a limited lifespan with the intention of encouraging consumers to purchase it again. In the case of ICT equipment and products, specifically, these themes are intensified due to the unknown rate at which these gadgets become obsolete due to technology advancements which necessitate guaranteed replacement. This has led to an enormous increase in the generation of related waste, an estimated 50 million tons of which is now generated globally each year, with the number expected to keep growing in the coming years. While this makes e-waste one of the fastest growing waste streams in the world, the rates of e-waste recycling, refurbishing or reuse, such as under a circular economy, are still very low. A circular economy centers around the reuse of products and raw materials, and the prevention of waste and harmful emissions. The effective recycling, refurbishing, reuse of e-waste reduces the need for continual new resource inputs, and has been shown to have a direct positive impact on the environment, economy, and society. Recycling e-waste offers direct business development opportunities for communities, thus contributing to job creation and recovery of precious resources. With the world's population continuing to grow, the demand for raw materials is growing in tandem, even though the supply of crucial raw materials is limited. Needless to say, extracting and using raw materials has major adverse impacts on the environment. These include increases in energy consumption and CO2 emissions. Whereas, on the other hand, smarter use of raw materials under a circular economy model may even lower CO2 emissions. It is estimated that e-waste prevention, eco-design and reuse may save companies billions of dollars. Other benefits include improving the supply security of raw materials, increasing competitiveness, stimulating innovation, and, as previously mentioned, boosting economic growth. The biggest challenge in achieving a truly circular economy, CE, is that most of the global economy is designed for linearity rather than circularity. Other barriers to achieving circular economy include consumers' expectations for convenience, lack of proper waste infrastructure, underdeveloped recycling technology, the use of wrong business models, doubts as to circular economy's achievability, costs of switching to circular economy, rooted culture, and lack of strategic guidelines and standardization. At the global stage, circularity is taking center stage and is being encouraged through international instruments such as the United Nations 2030 Agenda for Sustainable Development and the Connect 2030 Agenda. Circularity and the issues that lead to its need impact nearly all Sustainable Development Goals, SDGs, in one way or another. However, 3 SDGs, in particular, that are closely linked to the concept of a circular economy are Goal 8, decent work and economic growth, in which Target 8.3 aims to promote development-oriented policies that support productive activities, decent job creation, entrepreneurship, creativity, and innovation, and to encourage the formalization and growth of micro, small, and medium-sized enterprises. Recycling and refurbishing of e-waste can create new employment and contribute to economic growth. Goal 11. Sustainable cities and communities, in which Target 11.6 aims to reduce the adverse per capita environmental impact of cities by paying special attention to municipal and other waste management, since over half of the world's population lives in cities. Rapid urbanization requires new solutions to address rising environmental and human health risks, especially in densely populated areas. Most e-waste will be generated in cities, and it is particularly important to properly manage e-waste in urban areas, improve collection and recycling rates, and to reduce the amount of e-waste that ends up in dump sites. By reducing the consumption of finite resources in the most populous areas on Earth, i.e. cities, a circular economy can truly help contribute to meeting the needs of citizens in a way that is sustainable. Goal 12. Responsible consumption and production, in which Target 12.5 aims to substantially reduce waste generation through prevention, reduction, repair, recycling, and reuse. An increasing number of people on the planet are consuming growing amounts of goods, and it is critical to make production and consumption more sustainable by raising awareness levels of producers and consumers, specifically in the area of electrical and electronic equipment. The Connect 2030 Agenda is another instrument vital to globally implementing a circular economy and the reuse of electrical and electronic waste. It is a global initiative headed by the International Telecommunication Union, ITU, that sets out the shared vision, goals and targets for the global telecommunication, ICT development which the UN member states have committed to achieving by a certain time. The Connect 2030 Agenda promotes universal, secure, reliable, and affordable connectivity as key to accelerate sustainable development worldwide to achieve universal connectivity by 2030. Sustainable digital transformation by 2030, in particular significant improvement in tech and telecom contributions to climate and environmental action. This will have the effect of fostering circularity in the economy by eliminating waste and the continual use of resources. Other important bodies and work guiding the reduction of e-waste and supporting the implementation of a circular economy include the UN E-Waste Coalition, that ITU is part of, which calls for increased collaboration, building partnership and supporting member states to address the global e-waste challenge and advance a circular economy via 3 core functions: advocacy, knowledge, and intervention. The United for Smart Sustainable Cities, U4SSC, initiative by the ITU and UN, which provides an open platform for city smartness and sustainability progress. That includes a focus on optimizing recycling levels. The Green Digital Action launched at COP28 puts e-waste and the circular economy at the heart of a global collective effort to ensure the digital revolution supports global climate and sustainability goals. As a collaborative initiative, it offers a platform for cross-sectoral cooperation, essential for tackling complex issues like e-waste and building a more sustainable digital future. The International Telecommunication Union, ITU, which we have introduced briefly when discussing the Connect 2030 agenda, is the specialized agency at the UN for all information and communication technologies, ICTs. ITU's work is very comprehensive overall, a big part of which is standardization via its Telecommunication Standardization Sector, ITUT. Within ITUT, Study Group 5, SG5, is the lead expert group on developing standards and guidelines to tackle e-waste worldwide and achieve a circular economy, CE, globally. Events such as the annual Green Standards Week and the Symposium for ICT, Environment, Climate Change and Circular Economy act as a global platform where policymakers, field experts, city planners, regulators, standards experts, civil societies, and others can come together to discuss the role of information communication technologies, ICTs, and frontier technologies in facilitating environmental sustainability and climate action. Additionally, the Green Digital Action, GDA, initiative, led by ITU, is a multi-stakeholder collaboration to step up climate action across the global digital community. Several other events similarly hosted by ITU serve to raise awareness on the intersection of technology and climate change and the environment, including around issues such as e-waste and the circular economy. ITUT Study Group 5 has developed a variety of recommendations related to the circular economy, and is in the processing of developing more, that can be seen on this slide and the next.
ITUT Study Group 5 has developed a variety of recommendations related to the issues around e-waste, ICTs, and the circular economy, and is in the process of developing more. These can be seen on this slide and the next. In this presentation, we will be focusing on the 6 recommendations that fall under the ITUT L1000 series that is circled in red on the chart. The L1000 series recommendations are designed to ensure that the universal power adapter solution operates within the recognized current and voltage safety parameters by adopting existing ICT device technologies and by considering operators, manufacturers, and associations working within the market. All the recommendations have been set with the aim of reducing e-waste and increasing usability.
In this presentation, we will be focusing on the 3 recommendations circled in red. Recommendation ITUT 1020, Circular Economy. Guide for operators and suppliers on approaches to migrate towards circular ICT goods and networks. Recommendation ITUT 1022, Circular Economy. Definitions and concepts for material efficiency for ICT. Recommendation ITUTL Supplement. 28. Circular Economy in ICT. Definition of approaches. Concepts and metrics. Recommendation ITUTL 1023. Assessment method for circularity performance scoring.
ITUT Study Group 5 has developed a variety of recommendations related to the issues around e-waste, ICTs, and the circular economy, and is in the process of developing more. These can be seen on this slide and the text. In this presentation, we will be focusing on the 6 recommendations that fall under the ITUT L1000 series that is circled in red on the chart. The L1000 series recommendations are designed to ensure that the universal power adapter solution operates within the recognized current and voltage safety parameters by adopting existing ICT device technologies and by considering operators, manufacturers, and associations working within the market. All the recommendations have been set with the aim of reducing e-waste and increasing usability.
This slide is also a continuation of other ITU standards on e-waste and circular economy. We will start with recommendation ITUTL 1020. This recommendation suggests approaches of circular economy for ICT goods and networks. It focuses particularly on the next steps in improving circularity in the operator's supply chain. The objective of this recommendation is to provide options to improve circularity and to enable operators and their suppliers to create business models for the promotion of circular networks for an optimum solution that uses all the loops of circularity, from sharing to recycling. The next is recommendation ITUTL 1022. It contains a guide to circular economy aspects, parameters, and metrics based on current approaches, while considering their applicability for ICT. This recommendation discusses the special considerations and challenges in a broader context for all ICT defining parameters, metrics, and indicators with the intention of guiding the vertical standardization of the material efficiency for ICT. The guideline aims to examine the kinds of standards that are available and to assess their relevance for ICT product groups. And the following is ITUTL Supplement 28. This report investigates current approaches, concepts and metrics of circular economy and resource efficiency, and their applicability for the ICT infrastructure goods. This Supplement 1 introduces circular economy and resource efficiency. 2. Describes circular economy as used in the ICT industry. 3. Describes existing circular economy and resource efficiency metrics and examples of their use. And 4. Proposes next steps in circular economy and resource efficiency standardization. The last standard in the presentation is ITUTL 1023. This recommendation defines a methodology for assessing the circularity score of ICT goods. It introduces a 3-step approach to evaluate product circularity, helping identify gaps and areas of improvement. The aim is to support designers and manufacturers in selecting the most relevant circularity criteria during product development to enhance overall sustainability. To achieve circularity, business operations are encouraged to minimize their material impact on the planet and its natural resources, in an endeavor not to deplete them further and to remain within the limits of what the planet can generate or restore by itself. To realize the objective of achieving close to 100% circularity, businesses should develop circular projects considering the following 4 focus points. 1. Reduce the use of virgin raw materials through virtualization and automation of networks to reduce the environmental footprint, migration to software and service-based business models rather than hardware models, dematerialization of DVDs, CDs and newspapers by replacing them with connectivity-enabled digital media, and using recycled and bio-based materials where possible. 2. Extend Extend the use of products for a longer operating lifetime and use them more efficiently. Extend the lifetime of goods and networks by designing them for a longer operating lifetime. Increase or optimize rates of utilization, and minimize the impact on the planet by finding a balance between the longer operating lifetime and the introduction of more energy-efficient ICT goods, possibly based on new and more sophisticated materials. 3. Reuse and recycle. Improve second life of products and materials. Use of goods and/or materials that have been designed to be recycled, i.e., designed with a life cycle perspective in mind. Increase the reuse of products, as reuse by customers or suppliers is the best choice for returned goods to expand the total lifetime. Reuse could take place in the country where the product was originally purchased or in another country, in case the product is reused in another country. The company that sends the product to the other country should properly track that the end-of-life treatment of the product is taken care of as it would have been at the original place of usage. If the other country does not have proper end-of-life treatment facilities, the product should be shipped elsewhere for proper treatment. Repair and refurbishment of returned goods and goods intended for reuse should be arranged in a way that supports the circularity. Choose reuse over recycling when possible. And landfill should be avoided as much as possible. 4. Energy efficiency. Businesses should investigate ways to further enhance the energy efficiency of network infrastructure and end-user equipment. Businesses and other relevant parties should jointly develop initiatives for a circular business model, including implementation, planning and performance, such as undertake joint studies with operators and suppliers to investigate new business models to contribute to a more circular economy. Draw up a list of initiatives to achieve circular goals and setting joint goals on current initiatives. Plan quarterly meetings to monitor progress on circular initiatives, and set up. Select and monitor key performance indicators, KPIs, on circular goals. Circular economy is a wide-ranging concept which covers the full life cycle of both goods and business models. In general, circular economy is about closing the loop between different life cycles through design that enables greater recycling and reuse in order to use raw materials, goods and waste in a more efficient way and to increase energy performance. Thus, circular economy is associated with strategies to keep goods out of landfill and incineration. However, circular economy deals with both environmental and economic aspects. In an ideal circular economy, all waste generated would be reused as raw material in production processes. Discarded goods, therefore, represent a valuable source of raw materials. However, in practice, trade-offs have to be made with parameters such as reliability and cost. Resource efficiency is sometimes used interchangeably with the circular economy concept. However, resource efficiency focuses more on efficient use of resources and on minimizing the environmental impact of a good during its life cycle. An example of a generalized resource efficiency definition is dealing with the benefits obtained from the use of natural resources. Furthermore, materials efficiency is used in parallel with resource efficiency, or as a more precise concept dealing with raw materials only, excluding energy. Resource efficiency is, therefore, seen as a subcategory of circular economy and materials efficiency as a part of resource efficiency. As shown in this figure, the full life cycle of the good should be considered for both circular economy and resource efficiency. It is possible to influence all the most important aspects, minimizing material usage and environmental impacts, through the design stage. Goods can be designed to be used longer, repaired, upgraded, refurbished, remanufactured and/or eventually recycled instead of being thrown away. One important point of view is to avoid use of hazardous and rare earth materials when possible. In addition to reducing the materials, the focus is on energy usage during the whole life cycle of goods, which means improved efficiency in the production and use stages. Finally, in the figure, end of last life cycle means that the ICT infrastructure good can no longer be circulated. This figure signifies that business models are important for the success of the circular economy. Circular economy business models address circular supply chain, for example, biomass resources, recovery and recycling. For example, all waste is used for other uses. Lifetime extension of goods, for example, reselling, sharing platforms, for example, housing and transport. And product as a service, for example, tires by the kilo, leasing of equipment such as radio base station, etc. Business models in the context of ICT and the circular economy could refer both to ICT's own business cases, but also to how ICTs enable other sectors to introduce circular economy business models. As an example, cloud services imply per-servitization, for example, software, infrastructure, and platforms. Furthermore, they also enable a servitization of other sectors. For the success of the circular economy, the establishment of necessary business models and the relationships between various circular economy aspects is important. This figure demonstrates some of the previously learned concepts and relationships using an example of a procedure for returned servers. In the past, the whole ICT infrastructure good was first disassembled and subparts such as hard disks could only be reused separately. This method led to a relatively high share of scrap going to recycling instead of reuse. When testing of the whole ICT infrastructure good was introduced as an initial step, a higher share of reuse was experienced. This is illustrative of how a circular economy business model can function in real life. Here the circular economy aspects are sorted according to the first life cycle stage where the environmental impacts take place. In the first stage, raw material acquisition. Considerations include the following: recycled content. For ICT infrastructure network and parts of goods, recycled material content is an important indicator. However, there is need to consider versatile aspects beyond just simple mass. The recycled content indicator, metric as defined by ISO 14021, can be applied to ICT infrastructure goods. Although it should be noted that currently mainly secondary data is available. The amount of recycled content is challenging to estimate for ICT infrastructure. Most parts are bought on a global market, involving long supply chains, and the origin of the material content is not easily trackable. For this reason, the best assumption seems to be global average recycling data as found in ETS 203199 and ITUTL 1410. Additionally, cost is important to maximize the use of recycled materials and thereby the environmental benefits. Use of critical raw materials. Critical raw materials is a list of 20 materials, identified by the EU, combining a high economic importance to the EU with a high risk associated with their supply. Proportion of reused parts. The proportion of reused parts and subparts refers to the share of secondary parts of total parts of the ICT infrastructure good. For ICT infrastructure goods, there are high requirements on quality which might put restrictions on reuse of parts. High quality parts are required and there might be restrictions for secondary parts. However, some users may still be interested in reused parts due to cost advantages. Moreover, as innovation is fast in the ICT sector, reusing older parts might lower the energy efficiency of the ICT infrastructure goods. Reuse of mechanical parts, for example, standardized whole racks, seems more likely than reuse of electronic parts. Use of recycled materials seems a more promising way forward for the ICT infrastructure goods. In the second stage, use, considerations include the following: durability. Durability is about the ability of parts, modules or goods to maintain their functions and performances over their life cycle. That is, extension of durability is about extending the technical lifetime. For some categories of goods, maintained energy performance over time is a parameter that needs to be considered for durability. This parameter seems less valid for ICT infrastructure goods whose energy performance is not expected to worsen over time. Long durability is seen as a desired characteristic, however. Striving for durability and longer lifetime might also have disadvantages such as use of more sophisticated materials, changes in sales opportunities and locking users into an old design with limited performance, as durability implies the extension of operating lifetime. Such an extension often requires a trade-off with replacement of goods to minimize environmental impacts. Additionally, the durability of the good needs to be considered in relation to the technical evolution. Currently, the durability of the ICT infrastructure goods may well exceed the lifetime needed due to innovation. Upgradability. A higher upgradability reduces the need for replacement and increases the lifespan. Software upgrades are commonly done for ICT infrastructure goods. In terms of hardware, ICT infrastructure goods are generally designed in a modular way to ensure upgradability, e.g., empty slots for capacity expansion. More specifically, ICT infrastructure goods are increasingly designed for replacement of key parts according to the technical evolution and capacity. This way, the hardware, for example, a sub-rack, is more efficiently used. Removability. A high degree of removability is required for efficient repair or upgrade, and may also improve refurbishment and recycling efficiency. It could also extend the lifespan of the good by facilitating repair and maintenance. For recycling, it is assumed that especially parts made from or containing valuable materials, especially critical raw materials, are of interest. These parts are therefore a main target for removal, either through automatized or manual processes. The removability for recycling need not necessarily be high in modern, highly automatized recycling processes. However, a certain degree of manual removability might impact the quality of the recycled materials, and thereby the value of the materials. Some design tools have used virtual reality interfaces to simulate assembly, disassembly operations during the initial stage of design. Removability or removal efficiency can partly be measured by the time it takes to remove a certain part with a certain tool from an ICT infrastructure good. Repairability. ICT infrastructure goods are usually associated with considerable investments. Consequently, repair is a self-evident activity within ICT infrastructure operation and maintenance. The repair is facilitated by the modular design of products and appropriate removability. Repair flows are thus already established. In the last stage, end of life, considerations include the following: reusability. Reuse is generally seen as a preferable end of life option. However, the ICT sector evolves so quickly that reuse is not always recommendable. For example, introduction of more energy-efficient goods may be delayed due to reuse, lifetime extension. On the other hand, the reuse of ICT infrastructure goods might result in less environmental impacts compared to the replacement, so the balance between reuse and modernization needs to be carefully considered and may differ between goods. An indicator that can be used to measure reusability is percentage in mass of the part, good that is potentially reusable. In addition to this reusability rate, There are indicators that try to estimate the environmental benefits of having a higher reusability. The cost benefits could probably also be estimated. Recyclability. Due to its functional and unique mix of materials, each good provides specific opportunities for recyclability optimization. Recyclability indicators include percentage by mass, mass fraction in percent, of the component, product potentially able to be recycled, reused or both, sum of recyclable mass of each part, divided by the mass of the good, percentage in mass of the part, good that is potentially recyclable, the share of materials from a good that are expected to enter the recycling stream. Recoverability. Recovered materials are defined as material that would otherwise be disposed of as waste or used for energy recovery, but has instead been collected and recovered, reclaimed, as a material input. In lieu of new primary material, for a recycling or a manufacturing process. Recovery, therefore, covers both materials recovery and energy recovery. Materials recovery includes both reuse and recycling. Compared to reuse and recycling, energy recovery provides lower environmental benefits. Recoverability indicators include percentage by mass, mass fraction in percent, of the component, product potentially able to be recovered, reused, recycled or any combination, sum of recoverable mass of each part, divided by the mass of the good, percentage in mass of the part, good that is potentially energy recoverable by incineration, or recyclable. Refurbishability. Refurbishing is a process used, when needed, to prepare a good or module for reuse. Modules and plug-in units can be refurbished to a specified quality level, thus extending the lifetime of used ICT infrastructure goods or parts of them. Refurbishing is usually performed on whole modules rather than smaller parts. The quality of the good. Module or plug-in unit at end of life will decide if a relatively minor or more extensive refurbishment is needed. If the target good is in fine condition, a relatively minor refurbishing cost would be incurred, e.g. for cleaning. In contrast, a part in worse condition will incur higher refurbishing costs such as repair, replacement, etc. Sometimes refurbishment might not be worthwhile, and the good, module or plug-in unit will be recycled. Remanufacturability. Remanufacturing is usually performed on good or part level. Remanufacturing activities are likely to contain inspection, test, disassembly, rework, cleaning, reassembly, and reinspection. Remanufacturing primarily addresses goods, parts that do not meet the quality specifications. A remanufactured good should have the same or better quality as a newly manufactured good. Remanufacturing of complete ICT infrastructure goods to become like new is not seen realistic due to very high quality and reliability requirements, as well as the very fast technical development of ICT. The best option for remanufacturing for ICT infrastructure goods may be for simple mechanical parts. Several useful aspects, parameters, indicators and metrics have been proposed in literature from an ICT infrastructure goods perspective. The standards covered in this presentation reveal that the current understanding of circular economy aspects, parameters, indicators and metrics is still a bit scattered. However, it is clear that the circular economy quantification cannot be standardized for ICT infrastructure goods through one single aspect, for example recyclability, but should include several aspects. Parameters, indicators and metrics. Carefully selected aspects, parameters, indicators and metrics together can give a better estimation of the circular economy of a good during its full lifetime. Different perspectives should be considered like mass, environmental impact and economical value. It is likely that future standardization of circular economy will involve both generic and ICT-specific activities. For generic activities, cooperation between different SDOs is an option. ITUTL 1023 builds on the growing recognition that achieving a circular economy requires action from the very beginning, at the design stage of ICT products. Rather than only managing waste at the end of a product's life, this recommendation focuses on how we can make ICT goods more circular by design. It reflects a shift in standards, from end-of-life treatment to early-stage interventions that prioritize reuse, recycling, and resource recovery. To do this, the recommendation integrates key principles of circular economy into product design, using a concept known as Design for X, DFX. These include design for disassembly, so components can be easily separated. Design for recycling, so materials can be effectively recovered. Design for remanufacturing, so products can be restored to like new condition. Together, these guiding elements help reduce the need for raw material extraction and keep valuable resources circulating in the system for as long as possible. Following the guiding strategies, ITUTL 1023 provides a three-step methodology to help designers evaluate how circular a product is, and how it can be improved. The steps are simple but powerful. 1. Assess how relevant each circularity criterion is to the specific product. 2. Evaluate the margin of improvement, in other words, how much room there is to do better. 3. Combine those values to calculate a circularity score from 0 to 100%. This approach gives designers a clear picture of where to focus their efforts, and helps guide product development towards circularity and sustainability. To make this scoring system practical, ITUTL 1023 organizes circularity into three major aspects, each with its own set of measurable indicators. 1. Product durability. Is the product built to last? Is it robust, repairable, and supported by updates? 2. 3RUE. At the equipment level, can users easily repair, reuse, or recycle it? 3. 3RUM. At the manufacturer level, does the company support repair services, spare parts, and collection programs? Each aspect focuses on a different stage of the product's life cycle. And together, they provide a comprehensive view of circularity in design and support. Following the indicators introduced we saw in the previous slide, ITUTL 1023 further explains how these are measured using a structured relevance scale. Each criterion is assigned a level from R4, very high, to R0, not applicable, depending on how important it is for the specific product's design. This approach ensures the assessment is tailored and proportional. For example, battery longevity may be highly relevant for mobile devices, but not for fixed equipment like servers. By using a clear and consistent scale, the recommendation helps designers and stakeholders prioritize efforts and improve comparability across product types. Here is an example to show how this all works in practice. Using the L1023 methodology, the circularity performance of a 5G active antenna radio was assessed. This helped identify which aspects were strong, such as software support, and which needed further attention, like environmental footprint transparency. This is exactly what L1023 is designed to support, empowering companies to design smarter, more sustainable products, and helping the ICT sector move closer to circular economy goals. By applying the three-step process, from selecting relevant indicators to evaluating the margin of improvement, the product achieved strong scores across all three dimensions. 1. Product durability scored 87%, reflecting excellent robustness and long-term support. 2. Equipment level repairability and recyclability scored 70%, showing good performance with room to grow. 3. Manufacturer level support received 82%, highlighting proactive efforts like spare parts availability and service programs. This scoring process provides a clear and actionable picture, enabling both designers and stakeholders to focus efforts where they matter most, and demonstrates how targeted design improvements can lead to meaningful progress. Thank you for your participation in this course. We hope you found it informative and that you will join us in other courses that are also part of this series.